everyone, I'm Celeste Barnaby, and I'm going to be talking about our paper, Active Learning for Neurosymbolic Program Synthesis, which appeared at OOPSLA last year. So neurosymbolic learning is a paradigm that combines the flexibility of neural networks with the precision of symbolic reasoning. In particular, neurosymbolic programming languages use neural models to process unstructured data like images or text, and symbolic constructs to reason over the resulting predictions in a compositional and interpretable way. So let's look at this example of a neurosymbolic domain designed for image editing and search tasks. So here we have this user who has a travel blog where they share images from their camping trip. And while they're working on a blog post about their gear, this user wants to include some cropped images of people wearing backpacks. So manually searching through their library of thousands of photos would obviously be very, very tedious. So instead, the user provides a few examples of the types of cropped images they want, and a synthesizer learns an image editing program that can automatically process their entire image collection. Importantly, these programs combine neural perception, like detecting people in backpacks, with symbolic spatial reasoning over the detected objects. So here, this program finds all people in an image whose bounding boxes contain backpacks, and then applies a crop action to those people. So under the hood, we give the annotated images provided by the user to a synthesizer, which generates programs consistent with these examples. However, there may be multiple programs that match the examples while behaving differently on other inputs. So the key challenge becomes, how do we determine which program the user actually wants? Prior work in synthesis has aimed to address this issue through active learning techniques that query the user to clarify ambiguities. For instance, an active learning procedure may ask the user to annotate an additional image in their library. This additional input-output example may then allow the system to rule out programs in the hypothesis space and identify the user's intended program. However, when applied to neurosymbolic settings, active learning techniques may inadvertently return an unintended program. To see why, let's consider this example provided by the user, where the input is this image on the left, and the desired output is the cropped image on the right. To check whether a candidate program matches this example, the synthesizer first applies a computer vision model to detect objects in this input image. However, these models are imperfect. And in this case, the model detects the person, but misses the backpack. As a result, this program incorrectly produces a null output and is pruned from the hypothesis space, even though it actually matches the user's intended task. To address this issue, we use conformal prediction to explicitly model uncertainty in neural predictions. So instead of producing a single prediction, conformal prediction returns a set of plausible predictions that contain the true label with high probability. In this example, the model confidently detects the person, but is uncertain about the backpack. So standard inference would discard this low confidence prediction, causing the correct program to be pruned. In contrast, with conformal prediction, we can consider a range of confidence scores for which the detected object may or may not exist. In this case, conformal prediction may allow us to determine that the backpack may or may not exist in the image. Since the model is uncertain about whether the backpack exists, we can think of this image as having two different versions, one where the backpack does exist and one where it doesn't. We can collect these versions of the image into what is called a prediction set. In the context of neurosymbolic learning, we can use this prediction set to define conformal semantics for programs, such that every program returns an output set that is very likely to contain the ground truth label. So here, the output set contains a null value for the version of the image where the backpack doesn't exist, and a cropped image for the case where the backpack does exist. When we check whether this program matches the user's I/O example, we can check whether the user-provided output is contained within the output set. In this case, the correct cropped image is contained in the output set, so we wouldn't prune this program, which is what we want. When using conformal semantics, active learning becomes even more critical because the flexibility of returning a set of outputs can lead to an explosion in the number of potential solutions. A neurosymbolic synthesis problem can admit an intractable number of programs consistent with the conformal semantics. Neurosymbolic active learning refines the hypothesis space by asking questions that reduce ambiguity in the conformal prediction sets. So these questions target two distinct sources of ambiguity: First, ambiguity about the user's intended program, which we address by asking the user for additional input-output examples. And second, ambiguity about the ground truth labels of inputs, which we resolve by asking the user for specific ground truth labels in images. We can continue asking questions until there's no remaining ambiguity in the hypothesis space. So at a high level, our active learning loop repeatedly asks questions that refine both the hypothesis space of programs and the conformal prediction sets. In each round of active learning, programs are eliminated from the hypothesis space, either because the user provides new examples or provides a new ground truth label, which narrows down an output set. After refining the hypothesis space, we can check whether it's been fully disambiguated. If it has, we terminate active learning and return some program. If not, we select a new question to ask the user. So this work has three main contributions. First, we propose and formalize the neurosymbolic active learning problem. Second, we introduce constrained conformal evaluation, which allows us to reason soundly about uncertainty in neural predictions. And third, we implement these ideas in a tool called SmartLabel. So let's walk through an example of all of these steps. I'm going to use a running example in a simple visual arithmetic domain, where here the goal is to synthesize a program that counts the number of digits greater than 5 in a list of handwritten digit images. The DSL combines standard symbolic operators like map and filter with a neural perception operator, 2-digit, that classifies the digit images. In this example, the user labels this input list with output 2, since only 6 and 7 are greater than 5. However, the neural model misclassifies the second digit as an 8, so the correct program incorrectly evaluates to 3 and is pruned from the hypothesis space. This is exactly the kind of neural uncertainty that we want active learning to reason about. With conformal evaluation, we instead maintain prediction sets that capture the model's uncertainty about the second and third digits. As a result, this program now produces an output set containing both 2 and 3. Since the user's label is contained in this output set, the correct program is retained in the hypothesis space. However, under conformal semantics, many other programs may also remain consistent with the user's example. So here, let's suppose that our hypothesis space contains these 4 candidate programs. We want to determine which of these programs matches the user's intent. So given this hypothesis space, the next step in our active learning procedure is distinguish. The goal of the distinguish procedure is to determine whether 2 programs could produce different outputs under some assignment of the ground truth neural labels. In this example, the first program has output set 2, 3, while the second has output set 1, 2. So since there exists some labeling of the uncertain digits for which the programs produce different outputs, these programs are distinguishable and there's still ambiguity in the hypothesis space. So because of that, we continue to question selection. In the question selection step, we consider 2 kinds of questions that ask the user for outputs on new inputs, or questions that ask the user to label uncertain neural predictions. In this example, suppose our question space contains just these 2 label queries. Our goal is to select the question that eliminates as many candidate programs as possible. But since we don't know ahead of time how the user will answer the question, we select the question whose worst answer will prune the most programs, and we refer to this as the question's pruning power. To determine the pruning power of the first question, let's look at what will happen depending on how the user answers the question. So if the user labels x2 as 0, then we remove 8 from x2's prediction set, which means that the first program couldn't output 3, the second couldn't output 2, and the third couldn't output 1. Since 2 is no longer in the second program's output set, we would prune this program, since it doesn't match the user's given output. We use the same process to see what will happen if the user answers 8 instead. In this case, we find that the second and third programs will be pruned. So the worst answer of this question is 0, because it will lead to 25% of programs being pruned. Hence, the pruning power of this question is 25%. Meanwhile, the worst answer of the second program is 9, which will cause 0 programs to be pruned. Hence, we see that the first question is the better one to ask the user, because even in the worst case, we'll still prune 25% of programs. So after asking this question and receiving the answer 0, we now refine the hypothesis space. This is similar to how we check a question's pruning power, except now we have some definitive new information from the user. So since we know that x2 is 0, we know that we can safely prune the second program. A key challenge of this active learning framework is the overhead of conformal evaluation, because naively, it would require enumerating all combinations in the Cartesian product of the prediction sets of an input. Since the number of combinations grows exponentially, this quickly becomes an intractable problem. To address this, we introduce an efficient constrained conformal evaluation procedure based on bidirectional abstract interpretation. The idea is to propagate constraints both forward and backward through programs in order to prune infeasible elements of prediction sets early. Let's look at an example. So here's the AST of a program that counts the number of digits less than 4 in a list. We want to know whether this program's output set contains 2 without having to enumerate all possible combinations of labels. First, we begin abstract interpretation at the leaf node of the AST. The leaf node annotation is an abstraction of the conformal prediction results, with each prediction set abstracted by an integer interval containing all the elements of the prediction set. The abstract value of the next internal node is obtained by applying an abstract transformer for the filter operation. So the question mark after the second interval indicates that this item may or may not have been filtered, depending on whether its value is actually above or below 4. Finally, we annotate the root node with the abstract output of the program, which is the integer interval ranging from 1 to 2, depending on whether there are 1 or 2 items in the list. So now we perform backward reasoning, starting from the output to tighten these annotations. To start, we can tighten the root node annotation to the interval containing just the user's output value. So we know that the program outputs 2, and in order for that to happen, that means that exactly 2 items must have been filtered. So this second item that we were uncertain about must not have been filtered. Since this item must not have been filtered, we can infer that its value must have been less than 4, so we can restrict this interval to 0, 3. And now, when we perform conformal evaluation, we can disregard items in prediction sets that don't match these inferred conditions. So in this case, we can throw out the 8 in the second prediction set. This means that we now only have to consider 2 options instead of the 4 we originally had. So now that I've discussed the core technical contributions of our approach, I'll share some details of our evaluation. We evaluated our tool SmartLabel on 3 neurosymbolic domains: image editing, image search, and the visual arithmetic domain that we've been looking at. In total, we evaluated 112 synthesis tasks. Each task included a fixed input space, question space, and hypothesis space of programs. Across domains, tasks contained roughly 200 inputs and 800 questions on average. To construct the initial hypothesis space, we sampled 2 input-output examples and performed synthesis up to a fixed AST depth. The resulting hypothesis spaces contained roughly 1,500 candidate programs on average. To evaluate the accuracy of SmartLabel, we compared it against 2 active learning baselines from prior work, SampleSci and LearnSci. Because these approaches do not model uncertainty, they may incorrectly prune the ground truth program from the hypothesis space. Across all benchmarks, SmartLabel achieves 98% accuracy compared to 65% for SampleSci and 58% for LearnSci. Next, we evaluated how many rounds of user interaction SmartLabel requires to identify the correct program. We compared our worst-case pruning objective against 2 alternatives, optimizing for the expected pruning power and selecting questions uniformly at random. Overall, our strategy requires the fewest rounds of user interaction, converging in roughly 5 questions on average. Finally, we performed an ablation study where we used a naive version of conformal evaluation that doesn't use our forward-backward abstract interpretation approach. And we found that this ablation roughly doubled the average time of interaction. So to conclude, SmartLabel uses targeted active learning queries to eliminate ambiguity in neurosymbolic synthesis tasks while reasoning soundly about neural uncertainty. More broadly, we think that active learning is a promising way to make synthesis systems more reliable and trustworthy in practice. So thank you, and I can take questions now.
Okay, questions?
So I'm surprised you needed an abstract interpretation for the CCE. Is that CCE?
Yes.
Yeah. Can't just SAT solver do it? I presume these are small programs. The SAT solver should be able to figure out whether there exists an interpretation of each of them in the set such that it evaluates correctly.
You're proposing using a SAT solver instead of abstract interpretation?
Yeah, or an SMT solver, yeah.
For the visual arithmetic domain, like it's pretty simple, but for more complex domains like the image-based domains, it was more complex.
I see, okay. And your abstract interpretation is for those domains as well?
Yeah, so to instantiate SmartLabel on a specific domain, we require the user to provide like an abstraction with forward and backward transformers.
Okay.
Okay, more questions?
Hi. So if I understood correctly, the questions you ask are mostly about the labels and the uncertainty that comes from the neural model. Do you sometimes ask questions that kind of, combine separating multiple symbolic parts of the program and the neural programs together? Or could there be a question that slices both of them?
Okay, so we had two types of questions. A question could ask you about a specific object where there's uncertainty and ask you like, is this actually a backpack? Or it could ask you, like give you a new image and ask you to perform your desired edit. You're proposing something that kind of combines those two.
I guess. I'm asking if that's possible. Or
It is possible. For an interactive tool, we wanted to make sure that the questions were like realistically simple for a user to be able to answer accurately. But I think that is an interesting space for future work to explore other types of questions that you could ask.
Thank you.
Okay, more questions? So I have maybe a more curiosity-based question. When you talked about the metric for whether it's a sort of a strong question, that sort of reminded me of sort of like an information theoretic interpretation of this, that you want to reduce uncertainty the most. Like what's the most informative question that you can ask? Have you thought of an information theoretic interpretation of that aspect of your mechanism?
We did not think about it from an information theoretic perspective, at least I didn't. That's interesting. Yeah, an important principle is that as you answer each question, you're like making progress, like you're eliminating at least some programs from the hypothesis space. So that was our framework.
Yeah, in information theory, it tends to be more of a continuous, like you're updating your posterior distribution based on the questions, so that might allow you to also get rid of the sort of, actually, another question I have is how do you choose the threshold at which sort of the uncertainty counts as, like your example was if it was 20%, it was counted as not, and 70% was.
Yeah, that's a great question. So that's we use like existing conformal prediction approaches for that. So the threshold is learned from a calibration set of labeled data with respect to a specific coverage rate provided by the user. So like the user provides the calibration data set and says, I want to make sure that the prediction sets contain the ground truth with at least 99% probability. And you can learn the threshold based on that. And like intuitively, the tighter your bounds, the bigger the prediction sets will be.
Okay, great. Thank you. All right, if there's no more questions, we can wrap up this talk. Thank you.